So a lot of what we are doing when dealing with normal distributions is flipping between our x variable, the problem setting, and our z variable. So we use our table. As long as I'm working with that z table, I'm using one curve, and all that matters is what my setting is. Problem number 26. High school students across the nation compete in a financial capability challenge each year by taking a National Financial Capability Challenge exam. Students who score in the top 20% are recognized publicly by the Department of the Treasury. Assuming a normal distribution, how many standard deviations above the mean does a student have to score to be recognized? I want to figure out the z value, because I'm asked about standard deviations, that goes with that top 20% line. So really, I'm asked for what value of z is the probability that I get a score greater than that number equal to 20%. How do I find z0? Lots of choices. But it's assuming a normal distribution. Start with a picture. Draw me that normal curve, and let's figure out what part we shade and what we want. Felix? It is symmetric. But top 20% means that I'm looking for this value so that this part is 20%. Okay. I want to know what Z0 is. I'm going to look something up on my table. Do you want to use table C1 or table C2? Either way, we're in the appendices. That's where I do my setup. I want to use table 1. All right, table 1, first thing I do is I remind myself by looking at the picture. Table C1 gives me these pieces. So if I use table C1, I can't look up this part. I have to look up this part. So what's the size, the area in this part? Tony? Almost. 0.8 goes all the way off to the left, and this stops in the middle. So I want this bit. Because that's only half the picture, right? So that side, that right side from the middle over, that's 0.5, and I'm taking away 0.2 of it. So I want, in table C1, I want to look up 0.3. Now I could use 0.8, but if I was using 0.8, I'd be looking up the whole thing, right? So it would be 0.8 in table C2. So I can use either one. So let's find the closest number to 0.300. Actually, there are 4 decimal place numbers in the table. What's the closest thing to 0.300 in table C1?
0.1179.
Yep. I want to look up the number in here in the middle of the table that's closest to 0.3000. I see numbers around 3,000 around here, right? 35, 32, 23. Ah, 2967, 302. There we go. 2995. That's the closest value to 3000.
The left top.
That's when I have the Z. I'm looking, I've got the area this time. I'm looking for the Z. It even says on the outside here that those are Z numbers. Z numbers are on the outside, areas are on the inside. This is working backwards from the area, give me the cutoff. So in this case, when I get that closest to 3, the Z value is 0.84. Now, if I was working with table C2, I'd be looking up 0.8, right? So let's flip the page and start looking at table C2. And I notice that no matter where I am on this page, the first page of table C2, all of these numbers are small. The biggest number on this page is only a half. So I need to be on the second page. And when I start looking for 0.8, the closest number is 0.7995. And notice that's 0.84 again for my Z value. Now, technically, that's not 0.8, it's 7995. It's off by a little, right? If I want a little more area, I should move just a little bit smidge to the right. Just a tiny. So if I were to ask my technology, hey, how do I find the Z given the area? I can do that on here or in Excel. In Excel, when we were asking for areas, we used the normal distribution command. Well, now since I'm working that backwards, I'm going to use the normal inverse command. And in Excel, that's actually the command. Normal inverse. You give it A, mu, and sigma. Now, we were using the standard table, so we could tell it to go normal. Oh, use the standard inverse, and then you only have to give it A. On the calculator, it's in the same place as the distributions are. So if I hit that distribution button right here, above the variables in blue, it says DISTR. Well, look there, right at the top are the normal PDF, the normal CDF, and the inverse normal. Now, this inverse normal behaves like table C2. Behaves like table C2. So this is automatically cumulative, which means I don't need to give it 0.3. What do I need to give it for an area? 0.8. Now I can give it the mean and the standard deviation, but if I'm using the standard normal curve, those are 0 and 1 respectively. And there's my 0.84. Notice it's just a tiny bit bigger, 0.8416, because we had to go from 7995 to 8000. So the command in the calculator automatically works like the CDF. The command in Excel doesn't.
Where were the tails? Like where we put the tail? Like which select should we get for the tail? Mine says it says tail and it says left, center, right.
That sounds like a different test. Did you hit the distribution?
The other stuff, just the bottom parts has to be which side of the tail.
That's new. Oh, they made an update to the software. May I? When in doubt, we'll experiment. So I'm going to make the assumption that the 0.8 piece I want is the left. Because if you look at this picture, the 0.8 piece I want is the left side, right? So if I tell it to do that, yeah, it gave me that number. What if I tell it to do the right?
I actually need to do the 0.2 instead of the 0.8.
Let's find out. I'm going to tell it. Oh, I can't make that change here. Distribution, inverse normal. Let's make it right. What did it do? It flipped the picture over 180 degrees, didn't it? So I want 80% of the area, but I'm starting up here on the right. That means I end up over here on the left side of 0, don't I? It just turned the picture over. Now, center, what would center do? Center would give me the middle 80%, wouldn't it? So what would it cut off on each end? This is our trimmed mean idea. We've done this before. What would it cut off on each end? 10 on each end to give me the 80 in the middle. That's going to give me very different numbers, isn't it? Yeah, let's use left. Hey, they added something new to the updated version of the computer. That's what I get for using a calculator that's older than some of you are. Actually, I take it back. I think this one's only 10 years old. 12, something in that range. Now, what's interesting is that it said they give you the top, they take the top 20% of students. They didn't give me a cutoff score. I'm grading this exam. And I was told by the people grading that the average this year was a 70. And the standard deviation was a 12. I have literally pulled those numbers out of thin air. What's the cutoff score for being nationally recognized? Well, now this is the setting of the problem. As opposed to asking how many standard deviations up I need, now I'm asking about points on the exam.
6 points.
How did you get that number?
Just multiply 70 times 0.8 or 0.8 and then 80%. Well, possible.
But that would be 80% of the average.
Oh, it's the average.
Right. So let's take a look at this picture again. Where's, in terms of the scores, where's the 70 go? The 70 goes here at the average. So I want to know a number above the average. Tony?
Uh,
How did you get that number?
70, well, I took the 0.84 and multiplied by 12. It's
Aha. Our z-score is the average minus the standard, the value minus the average over the standard deviation. So if I know this time the z-score is 0.84, then that's x minus 70 over 12. And then that's exactly what I do to solve for x, is I multiply across the 12. And then I add the 70. And 80.08 is exactly what I get. Maybe next year, the average will be higher or lower because they changed some things on the exam. The standard deviation will be wider because there were some really good and some really bad people pushing the width of my picture further out. If these change from group to group, I can still say, what's the top 20%? Assume a normal distribution. Problem 39. The time required to verify and fill a common prescription at the neighborhood pharmacy is normally distributed with a mean of 10 minutes and a standard deviation of 3 minutes. Find the time for each of the following events. I want my fill to be in the highest 10%. What time is the cutoff for the highest 10%? Similarly, middle 50, highest 80, lowest 10. These are deciles, aren't they? Only we're not doing it like we did deciles, like we did quartiles and median, because we're not using order. We're using the normal distribution instead. So the two critical pieces of information I need to start with for this problem is that the mean is 10 minutes, the standard deviation is 3. Find the time to be within the highest 10%. Before we actually find the value, tell me what I need to do.
Take the 9.9, try to find that on your C2 chart to find your z-score.
I'm going to look at the picture again. I am a visual person. Every time I start thinking about, I know an area, find me a boundary, or I know a boundary, find me an area, the picture comes to my head. I draw these stupid little normal curves all day long doing statistics like this. So I draw even a crappy picture is better than no picture at all. Highest 10% is going to be way up here with this part being 0.10. So the rest of it is 0.90. That's using table C2. Using table C1, what number would I use? 0.4, because I'd ignore this half. I only use the place between the center and our right edge. Now, that's not the only way to do it, even with table C2. By the way, 0.9. 0.9, here we go. Closest I can get is 0.8997, which is 1.28. But that's a Z. And we were asked for a time. How do I get there from here? Hang on.
Go to
The time required to verify and fill a script is normally distributed with a mean of 10 and a standard deviation of 3. Find the time for each event, highest 10%. That part?
Yeah.
Okay.
1.28 going from like average. So let's please go on the average.
Ah,
10 minutes.
right. So again, I'm doing this conversion. Z is X minus the average over the standard deviation. In our case, that's X minus 10 over 3. And I know the Z score to be 1.28. So I multiply by 3 and I add the 10 to get X. Almost 14 minutes. $13.84 minutes. Now it said highest. These are the ones that take the 10% longest. Takes 13.84 minutes or longer. I kind of object to the use of the word highest here. Because we're talking about time, I would have said longest or shortest, but that's me. All right. Same question. Middle 50%. Again, let's draw a picture. This is Z equals 0. Middle 50, the middle phrase is the middle here, center. If I want the center 50%, I'm going to have 2 bars. But those 2 bars will be the same distance to the left and the right.
Both sides.
Aha. So each half of that shaded region is 0.25. So I could use table C1 to find 0.25 right there. area is 0.25. I could use the center version here, and it would give me both sides. But since it's symmetric, it probably will only give me one number. It'll probably either give me just the positive one or just the negative one. Since I don't have the center option, you should do that and tell me if that's what comes up on your calculator. But if I do the inverse normal, if I'm going to use my calculator operates like table C2. If I'm doing table C2, what number do I want to put in? To find this bar, what number would I put in? Because I need to add the other half over there. Now, if I do that, inverse normal, right here, it's going to be 0.75. Is that the number you got?
So I did
The 0.5 in the middle.
center, gave me the negative, and then it gave me the positive.
It'll give you both of them.
Yes.
Oh, that's really nice. But I know it's symmetric, so I know it's this one on the left and it's negative this one on the right and the negative of this on the left. Ooh, that's good. That's nice. I like that. But now I know this has a z-score of 0.675. I'm rarely going to go any more than 3 decimal places because if I was in my table, I'd only have 2 decimal places, right? Let me look at the table for a second. We're talking about 0.25, yes? In my table, it was a lookup of 0.25. When I look up 0.25 in here, what I find is these two numbers. And they're just about the same distance from 0.2500. This one is 14 left, this one is 17 up. So it should be right in the middle between those. Well, between 7 and 8 is 675. We can interpolate between. I don't like doing that as much because this isn't a straight line. So I'd rather use my technology to try and find a more exact number, but I really am not going to go any further than 3 decimal places because I only get 2 for my table anyway. Hey, wait a minute. That means symmetrically over here, z equals negative 0.675, which, by the way, I could have found that one directly also. If I'd used table C2, I could have started all the way on the left and got up to there with what area? What's the area of this white unshaded piece here? If the shaded side is 0.25, then the outside is 0.25 since the whole side is a half. Wonderful. And again, if I use table C2 and look up 0.25, there you go. It's right between those, which is -6 between 07 and 08, exactly the same number. But again, I wasn't asked for z-scores. I was asked for times. I got to go through this again twice. The low time is 10 plus 3 times negative 0.675. And the high time is 10 plus 3 times positive 0.675. Give me some times, Tony.
7.9. The other number was 12.02.
Works for me. I think I have, with mine, I got 975.
I just did it with the calculator. I was still.
Sure, that's fine.
Second number.
12.02. All right, note to self, get a darker blue. Now, I could take this same setting and ask for the fastest 10% of filled prescriptions. Well, fastest in this setting would mean a low number, right? A smaller time is faster than a larger time. So we have to take the idea of the setting of the problem to decide which direction we want to go. Questions? Problem 44. The credit scores of 35-year-olds applying for a mortgage at Ulysses Mortgage Associates are normally distributed. Mean of 600, standard deviation of 100. What's the upper 5%? Higher credit scores are better. It's not a question, that's a statement. Lovely spinning beach ball of doom. What's our critical threshold mortgage score? Be in the top 5% of qualified applicants at age 35. What do I look up? What do I do with it once I got it? Jason. So whatever's closest to 0.45 in what? In C1, because I'm starting with the middle. If I was starting all the way on the left, I'd use table C2. But you said use C1. I'm going to try and find the number closest to 0.45. Yeah. Now, you look, it's right in between, isn't it? We'll use 1645 or we use 164. That's perfectly fine. Again, because it splits the difference just so perfectly. And now I need to find the X value. Z is X minus the average over the standard deviation. So X is the average plus Z times the standard deviation. You can work that formula out in advance if you want. Then all I need to know is which one I'm going from and to. So now I know this is 600, that's our average, plus the Z-score, 1.645, times our standard deviation. And I get 764 and a half. This particular mortgage company has a commercial that says 90% of our customers qualify for a mortgage. So to not qualify, your score has to be low. What's the cutoff for not qualifying? Again, draw me a picture. Tell me what your picture looks like. And then I pop up which table to look at and what thing I want to find where. Since having a high credit score is a good thing, having a low credit score is a bad thing. I'm not going to qualify if my credit score is low. Felix?
Look again at C1
Okay.
symmetric. Then I looked at what time like the 0.4 closest to 0.4 because less than 10% are remaining. And then I see score from negative like positive 1.28, but because it's symmetric, I look for score negative 1.28. Then I will be the same formula as the exercise.
Exactly. If I think of a low score as being on the left, then I can use 0.1 for table C2. For table C1, I'm going to have to use the 0.4, but table C1 assumes you're on the right. So I flip the picture over and it looks like this. And that'll give me the right number. That's exactly the right way to do it. Or I can use table C2, and in table C2, negative 1.28 is really close to 0.1, isn't it? Both work. The inverse normal command on my calculator will work. I can even go so far. Inverse. There it is, norm inverse. It's norm first. NORM dot. Notice there are two different inverses. There's norm inverse and there's norm S inverse. The S is the standard. That's the one that goes on my Z table. Dot INV. Now I give it the probability, which we just said was 0.1. And then I can put a 0 or a 1. And that'll give me a CDF versus a PDF. I'm pretty sure that's the one that works. Nope, that is the wrong one. I don't bother with that. It always gives me the CDF. There we go, negative 1.28. Ta-da! That's the number I wanted. So X is 600 plus negative 1.28 times 100. So that's 600 minus 128, which is 472. Ta-da!
Can I get that loan?
Oh, yeah. Yes, I'm sure you can get that loan with a very low credit score. I'm not sure you're going to want that loan at a 17.5% interest rate with a balloon payment and only a 6-year term. Yeah, we can talk about whether or not that's a good mortgage or not based on a low credit score. That's for the financial math class, personal finance, SBU 280 next semester, or SMA 104, make money matter. Questions? Other than, can I get the loan? Yes, sir.
We now using the normal distribution, but it always says the exercise. How can we assume that?
That's actually a really good question. How do I know whether or not the data I'm looking at is normal? Unfortunately, there's no guarantee. And it is one of the bigger questions in all of probability and statistics is, can I use this normal idea? It turns out that one of my favorite results is data that is collected by sampling, especially by repeated sampling, is normally distributed. So that's the best part. When I do a bunch of surveys, stuff works out to be normal. I just can't do the survey once and hope for the best. I have to look at multiple, or at least the same kind of survey as has been done before. Again, there are other distributions. There's our Poisson distribution. There's the exponential distribution. There's our triangular distribution. We're not going to do those because we're dealing with data collected from survey data. And that's what we're going to use moving forward from here, is the fact that collected data by survey is almost always normal, especially with very large populations. There are very few cases where we have abnormal or non-normal data, in which case it usually follows one of the other well-known distributions, things like waiting times. Waiting times are rarely normally distributed. Things like, I don't mean to scare anybody, but hard drives eventually do fail. When we test equipment, it's called the mean time between failure. But it's not actually a normally distributed idea. It's more of a decaying exponential graph, something we talk about in calculus. So we have a different curve and we need different areas. And again, if I look in my distributions, there are a lot of other distributions available to me. Poisson, geometric, binomial. There are some we're going to use later called the F, a chi-square, and these T's. These come up in different situations where we modify our normal curve a bit. We won't use geometric or chi-square or Poisson in this course. The general problem stats course covers them in a lot more detail. Right. So something like, again, I use waiting times. Waiting times is almost always Poisson. Exponential is things like oh, no. I'm sorry. I've said that now twice and it's backwards. Waiting times are exponential. Poisson is, I'm going to let you flip a coin. You win when you get heads. How many times will it take? So it's a binomial, but it's repeated. And I'm not looking at just one occurrence. I'm looking at a combination. Well, that changes my curve, doesn't it? So all of a sudden I end up with it. That's what Poisson usually is. So I'm going to do something until something happens. All right, our hard drive tester, right? I'm going to keep using the hard drive until the mystical gray smoke has escaped. Don't want that. One of my jobs as a graduate student at the University of Pittsburgh, I worked in the physics department where I smoke tested optical amplifiers. So they gave me a little circuit board and said, put it in here and run a test. And then take it and put it in the oven and bake it for a week. Actually, we're going to cycle the temperature because it's going to be heated and cooled repeatedly when it actually goes into production. And maybe some of the soldering joints will break out of. But they said if I ran this test for 7 days, then we would see all the stuff that was easily going to fail would fail out. And the stuff that had survived would have a much longer expected lifetime. So I did these things until they broke a week at a time in batches of like 100. But it was a really weird job. Was working for the physics department for Bill Cleland. Okay, the reason I want to use normal distributions is to do testing. Because I take a probability, it's an area in a curve, but then I ask, okay, I did a survey. Assuming my survey data came from something normal. Is my result unusual? Is my result an outlier? Is my result telling me that my assumption about the bigger group from which I took my sample is wrong? The purpose of understanding this curve is to test questions. That's what we'll start on Friday. And we'll see you all then. Homework for this chapter thus is due Monday. The exam is Wednesday. The review sheet is up. See you all then.